Okay, so far we learned about the characteristics of transducers. So we have static characteristics, dynamic characteristics, and we also looked at modeling of transducers from systems perspective. So if I look at a transducer, uh, I have the transducer here. I have the physical input. It could be pressure, temperature, displacement, acceleration, velocity, anything, and I have electrical output. This is how we look at transducer. Okay, the way that we can learn about transducers, we look at the input and study all pressure transducers, or we study all accelerometers, or we study all temperature transducers, right, or all flow transducers. On the other side, I can look at from the same transducers from the electrical characteristics and study all transducers that use a resistance for transduction, right. Similarly, I can look at all transducers that uses an induction method for transducers, or capacitive, right, for piezoelectric, right. So we can look at and learn about transducers in either from the input side or from the electrical output side. Being an electrical engineer, and it's much easier if I look at transducers from the electrical perspective, because then we can look at different inputs with the same electrical phenomena, how we can uh, use a particular, let's say, resistive type transducers for measuring temperature, or measuring pressure, or measuring force, anything, right. So we are going to learn looking from the electrical side. So first we will learn resistive type transducers, right. The resistive type transducers, if I look at a resistive wire, I take a wire whose cross section is A, the length is L, and let me put capital L, and resistivity is rho. So if I look at the resistance of wire of length L, would be, we have already learned this, rho L by A. So now I can use rho, I can use length, I can use area to change with respect to my physical input, and hence get a transducer. We will see A is normally not used in resistive type transducers for obvious reasons, because the resistance of the wire or resistance of the resistor is inversely proportional to A, and inversely proportional leads to nonlinear characteristics. So we do not want to have a nonlinear characteristics for any type of transducers, and we should avoid as much as possible using nonlinear techniques, because that creates a lot of other problems which we can avoid. Okay, so if I now look at, we are going to look at the length L. In fact, this is the simplest type of transducer. I take a resistive wire of length L, right? I have terminal A, terminal B, and I put a wiper, right, and I move this by displacement X, and this is terminal O. So if I take respect to O, I call this as E0 output. This is I connect a simple battery across terminal A and B. I have EB, right, and the total resistance RP would be rho L by A. If I look at Rx would be rho X by A, where X is the distance that is the wiper has moved in. So the moment I connect it, there is going to be a current I. I can write current I is equal to EB by RP, right? And so if I look at E0 is equal to Rx into I, right? The current I is flowing through it, and I have Rx across this, so voltage drop E0 would be Rx into I. So now so this would be EB by RP. RP I already know, rho L, capital L divided by A, that will go on top. Rx I know, rho into small x by A. So if we cancel AA, rho, cancel AA, rho, so I get E0 is equal to EB by the total length L into X, right? I have an output voltage which is simply proportional to the displacement X. Of course, we know this is a linear potentiometer, right? We use it for several circuit requirement where we need variable resistor, but in the transducer parlance we simply use this as a resistive type, resistive potentiometer type, displacement sensor. Right? Of course, I don't have to have linear displacement. I can just simply put the wire as right, and take the output. So this becomes B, this becomes A, this becomes O, right? And again E0 would be, if I connect a battery voltage across terminals A and B, would be EB by theta full scale, whatever is the theta full scale that I have bent the wire to, into theta, where theta is the moment. Okay. So the displacement can be linear displacement or angular displacement, right? So it's a very simple type of transducer. The signal conditioning circuit is also simple, and if I look at on the mechanical side, of course there is a mass. The movement is the wiper. Wiper has a mass and damping. It's normally frictional damping between the wiper and the resistive element, right? Uh, Nowadays we don't use, especially for small displacements, 5, 10 centimeters or even 20 centimeters, we use film type potentiometers. So where we have a thin resistive film is coated, and we have the wiper moving on it, right? So this is A, this is B, this is O. This is very popular. You can buy it for about 100, 200 rupees, and you get that. And in the earlier one, the film was carbon film. Now we no longer use carbon film because carbon wears out very fast, and also it has a temperature coefficient. Use certain type of metal, so we use a metal film potentiometer, which lasts a little longer than the carbon film, and which is also has a very small temperature coefficient, right? In that sense. Now, if I look at the electrical side, in the mechanical side, we already said there is M and D. So M in the electrical equivalent, I will get an inductance if I use the direct equivalent. D, I will get a mechanical. On the electrical side, it's just resistance, nothing else. So the equivalent circuit will be LM, RM on the mechanical side, and on the electrical side, potentiometer resistance. So this is a first order system, right? So this is the first order system. If I give a step input, we know that it slowly responds. So I have settling time. Okay. Now, if I look at E naught, so if I use the electrical equivalent circuit, so I have this EB by capital L into X, that's the voltage that is generated, right? So I am looking at from here, right? So this is EB. So if I look at the Thevenin equivalent circuit, I get a open circuit voltage would be X into EB by L, and the Thevenin resistance would be X into RP into 1 minus X into RP divided by X RP plus 1 minus X RP, totally RP, right? So this I can put it as denominator is RP. This is B, this is O. Sorry, okay. So if I connect a voltmeter which has a resistance RV, then the voltage will no longer will be E naught. So this will be E naught into RV divided by RV plus R Thevenin. This is R Thevenin, right? So the problem is R Thevenin varies as a function of X, right? Of course, E naught varies with respect to x, so this will be EB by L into x into RV by RV plus RL, and this is also x. X in the denominator gives a nonlinear. So in the earlier years this was a problem because most voltmeters, most measuring circuits had very low internal impedance. RV was only few hundred kilo ohms you can get, but in the electronics world of today we can get few mega ohms or few tens of mega ohms as RV, so it's not a big problem. If I use a 10K potentiometer and my measuring circuit has 1 mega ohm impedance, the nonlinearity will be small, but there will be some nonlinearity because of the loading, right? That you should understand. So the resistive potentiometer type displacement sensor, both angular as well as linear, is very popular, used in the industry quite a lot. There is only two problems. One is the friction between the wiper and the resistive element, right? So when the friction is there, you'll have to give enough force to move the wiper, which means the mechanical side there will be loading. Mechanical force is required to move the wiper. The second thing is, because of friction, there will be wear on the, either the brush will wear out or the resistive element will be wear out. So there will be a wear on that, which means the transducer will have limited operational cycle. So generally resistive potentiometer transducer manufacturer says that you can use my resistive potentiometer type resistive displacement sensor for about 1000 operations or as high as 10,000 operations, right? So the 10,000 operations is the kind of limit that you can get from resistive potentiometric type transducer. Nevertheless, if you are not really intending that there will be too many operations in its cycle, you can use a resistive potentiometer sensor, right? One place where it is used is the automobiles. You have what is known as a brake, and brake actually wears out because every time you apply a brake, it gets degraded. And there is a very small sensor called brake wear sensor. It simply informs how much of brake shoe is left, and that's a simple resistive displacement sensor, right? It is also possible, instead of using resistive film, we can use a resistive wire. So I take a cylindrical former and I wind wire here and put a wiper that moves on the wire, right? So we call this as wire wound resistive potentiometer type displacement sensor. The advantage of a wire wound resistive potentiometer is that you can slightly put a little thicker wire. Also, wire can be made non erosion type, and you can use a sacrificial brush as the wiper. So when something goes, the brush goes bad, you can simply replace the brush and continue to use, right? Multiple operational cycles you can get. But if you solve one problem in life, you will always introduce another one, if not two, right? So if I look at the input-output characteristics of the transducer, this is X, and let's say this is X is equal to 0, this is X is equal to capital X, full scale, right? And if I start moving X, I will get characteristics which is not continuous, which is steps. So if I have totally nt turns, each step, right, and I put the battery voltage here, EV. So this is delta V, where delta V will be EB by NT. For example, if I have 1000 turns and I give 1 volt, then delta V will be 1 volt divided by 1000, that is equal to 1 millivolt, right? Because the wiper can only move from one turn to the next turn. So you get the stepwise output. The resolution, we call it as delta V, is equal to EB by N. But if you actually build a resistive wire wound potentiometer, you will see that after it moves up and you have a small kink, and then, right? So there will be two steps in between, one step between the turns. The reason is, if I look at the wire, I am blowing the wire, we put the wire, right? This is a cross section here. If I cut, I will get this, and of course these are wires but insulated, right? Only one side where the wiper is there, it will be, right? So if I make the wiper like this, right, I have full end turns. It's possible to have the wiper like this. What happens? This turn and this turn are shorted. So here I will get NT turns, here I will get NT minus 1 turn fully, because the wiper shows two adjacent turns. This I am assuming the wiper to have only one diameter, have a length of one diameter of the wire, but in practice we give several diameters, it doesn't matter, it will always be NT and NT minus 1, right? So when it moves from here to here, you just kink. So this small, right, is called delta V minor, right, where we can derive. I'm not going to derive, this is not very. Delta V minor is equal to EB by X as usual into 1 by NT minus 1 minus 1 by NT into X, right? So as X varies, this is capital X. To avoid, I call this as X full scale, right? Easier. Let's not get confused. And we also have delta V major is delta V minus delta V minor, right? So just because you're getting some small kink, you should not think that is the actual output. It's not the actual output. The wire wound resistive potentiometer type displacement transducer suffers from the minor and major resolution pulses. Right? Again, this is not a big problem. We can continue to use this. Right? So we can make, as I said, linear displacement potentiometric type transducer or a linear angular type potentiometric transducer, measure angle as well as displacement x. Now we know that the one problem or the only problem in a resistive potentiometer is the friction between resistance and wiper. Right? Is it possible to eliminate this? For a long time people did not really attempt it, but we can. Let's assume this is the resistive wire. I can use a film or a wire wound, it doesn't matter. Now I don't put the wiper, I put it slightly away, there is an air gap, and I move this by x. So this is A, B, and this is O. So if I look at the equivalent circuit, I get between A and B, I'll have the resistance of the potentiometer Rp, and I will have the variable point with the coupling capacitor Cc. Let me write it clearly. Right. This is A, this is B, and this is O. Now, of course, I have a capacitance. The capacitance comes because of the air gap here, right? So one way is to say, okay, the moment it's capacitance, if I put a DC excitation, nothing will come out because capacitance will block DC, right? So I can instead use an AC source and get an output here, right? So if I look at here, please remember this voltage is X times EB by L, right? This voltage would be, we use the same, EB is now a phasor, so EB, this is E naught, again a phasor, so I call this as E naught, EB into X by L, that's an AC circuit. So I have the resistance Rp into X into 1 minus X divided by Rp, okay, Rp into X by L, 1 minus X by L, okay, Rp square. Okay, whatever is, this is A and B now shorted. I will have X times Rp, 1 minus X times Rp in parallel. So X times Rp into 1 minus X times Rp divided by X times Rp plus 1 minus X times Rp. That will be the value. And of course, I have the capacitor here, Cc. This would be the EC. So this would be the final E naught, right? Even though this voltage is directly proportional to X, this voltage, because of the series impedance, will not be, the moment I try to measure right, an AC voltmeter which has its own internal impedance ZV, the E naught would not be a linear one. That is mainly because the capacitance that we get would be in the order of picofarads, right? The picofarad means that 1 by j omega c, however omega is high, C in 10 power minus 12 will result in at least few hundred kilo ohms equivalent impedance for CC at that frequency. So, which means I would not be able to really use this circuit, even though I can excite it with AC, and my capacitor would allow AC to go on to the output side. It's not a good solution. Moreover, when I move here, I may get 1 cc. If I move here, right, I will get another cc. So the cc will actually vary depending upon x. That's another problem. How do we handle this? We use a signal conditioning circuit which would eliminate the effect of CC on the output. That is, I get an output which is independent of CC. CC does not affect my output. CC gets, I get an output only proportional to this. Is it possible to do that? Yes. In fact, there are several solutions. The very first solution was given by an engineer called Major. The published work is in IEEE Transactions on Instrumentation Measurement. I will put the reference on Moodle. You can download the paper and use it from our library. And it's a very nice, interesting circuit, but very complicated. They used what is known as a Martin oscillator, right, and really complex, right. There is a very simple circuit that is possible to use, where we have the transducer, right. So we connect one switch here, we connect another switch here, I am not drawing it correctly. Okay, this is not correct. So here we give plus VR, this is grounded, and this is grounded. I give minus VR here. Again I put a switch here. This is grounded. This one goes to an op amp, and we have a capacitor. This is CC, capacitor CF. I have the output, and now let me put, this is one switch, another switch, right. There would be a control to this switch. The control to this switch is again goes through another switch. So here I give a clock. So this switch is controlled by clock, and the control of this switch again goes through so this is go to clock, this is grounded, again this switch, okay, and here what we do is we give a comparator, op amp comparator, minus plus. The plus is given to another switch. We give plus VR here and minus VR here. The output of the so there is a switch here. So the output of the comparator controls this switch as well as this switch as well as this switch. All three switches are connected. Right now, this whole circuit works like a relaxation oscillator. We take this output and put an integrator and get E0. Okay. Now let us look at the operation. Assume that the position is like this. The position is like this, and this position will be like this, right? And so every time I give a clock, right? So if clock is 1, I assume whenever clock is 1, this is the position, right? So what is going to happen? B would be at minus VR, A is ground, so I will get a voltage sum here. I call this as V1, I call this as V2. So this would be at a particular point, Vx, right? Now that Vx is connected in this fashion. Please remember, this is virtual ground. So what will happen? The current would flow from output here to here to here to minus here, because this is ground, right? So the capacitor would be charged. Let's assume that right, let me reduce this so that so this is plus VR, this is minus VR. So I arbitrarily choose some point, capacitor will get charged. Now the moment clock turns 0, I will use the green for 0. This switch will become here. This is permanently connected. This switch would connect here, and this is again permanently connected, right? Only these two are clocked. So one end of this is connected to ground. The CC other end is also connected to ground. So the current will flow and discharge CC. Once again, when the clock becomes 1, the old position, this will be here, this will be here, and this will be here, and the capacitor CF will gain another plus. So this will go on till it reaches VR. The moment that it reaches more than VR, please remember, this is inverting input, this is VR. The moment inverting input is more than the non-inverting input, this will shift. So far it was plus VR, and the moment it goes this switch, I am talking about, I'll call this as V0. So this is V0. We'll switch to, this is plus VR, this is minus VR. Now the moment it switches to minus VR, what will happen? This will get permanently. Now what color I should use? I've already used most of the colors, so I'll use black. So this would be permanently connected here. This will go, because this will go here. So this switch will be clocked, and of course this switch will be clocked, right? So this would be permanently grounded. Okay. So now what is going to happen? The charging is going to happen with respect to plus VR. Now when I connect plus VR here, how will the current? The current will go out of plus VR. So which means the current now will go from plus VR in this direction, right? So which means the capacitor will be charged in the opposite direction compared to the previous condition. So when the charge is in the opposite direction, the capacitor will now discharge and reaches minus VR. What happens to after reaches minus VR? The once it reaches minus VR, the comparator will shift and it will go back to the same condition. So I will have steps again. So this keeps up happening. This will keep on oscillating like this. Now I call this as T1 and this as T2, right? Let's look at what is T1. T1, the voltage acquired is minus VR to plus VR. So T1 is voltage acquired is 2 VR divided by number of clock cycles in that. How do I get the number of clock cycles? For each clock cycle, I am going to have a stepping voltage of VR by 2 into 1 minus x by x full scale into Cc by Cf. Right? That's the step voltage that I am going to get. So this many times Tc will be there. So my T1 will be total voltage gained divided by voltage gain for each clock cycle multiplied by Tc. Similarly, I can easily write T2. Can you tell me what is T2? It's the same thing. I acquired 2 VR. Now it is going from plus VR to minus VR, 2 VR again. VR by 2 is what is applied. Now what happens in the current? It is charging in the opposite direction. So it will be 1 by x plus x full scale into Cc by Cf. Now if you remember, the output is integral of this signal 0 to T1 plus VR plus T1 to T minus VR. Please remember, here it is integrating plus T1, VR is integrated during T1, between the T1 to T, this is T, minus VR is integrated, right? So this, if you put VR, I can take it out. So this would be T1 minus T2 by T1 plus T2. Please remember, the total time is T1 plus T2. We already have T1 minus T2, right? So I can write E0 is equal to T1. You remember 2VR divided by VR by 2 into 1 minus x by x full scale into Cc Cf. Cf goes on top, right? T2 is minus 2VR into Cf divided by VR by 2 into 1 plus, here this is 1 minus, this is 1 plus, x by x full scale into Cc. Cc by Cf, Cf goes there. So I can even take this 2 in the denominator and put this as 4 divided by 4 VR Cf divided by VR into 1 minus x by this is VR into x full scale plus 4 VR into Cf divided by VR into 1 plus x by x full scale into Cc into Cc. So I can cancel 4VR, 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 Cf, 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 Cf cancel. again VR, 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 CC, CC, CC can be cancelled. So I can write this as E0 is equal to VR into 1 by 1 minus x by x full scale minus 1 by 1 plus x by x full scale divided by 1 by 1 minus x by x full scale plus 1 by 1 plus x by x full scale. Again, what we do is in E0 is equal to, I take the numerator 1 minus x by x full scale into 1 plus x by x full scale. I take the denominator here. In the numerator, I am going to get 1 plus x by x full scale minus 1 plus x by x full scale. Right? Similarly, in the denominator, I get 1 minus x by x full scale into 1 plus x by x full scale. Here 1 plus x by x full scale minus this will be 1 plus x by x full scale plus 1 minus x by x full scale. Again, I can cancel this and this, right? And x plus x by x full scale, this will be cancelled. So plus 1 minus 1 will be cancelled. So I will get 2 x by x full scale divided by 2. VR is already there. So VR into x by x full scale. Right? So we see that the output is VR is a constant, x full scale is a constant. So it is linearly proportional to x, and we see that the output is independent of CC. CC does not affect. So CC can be 1 picofarad, 2 picofarad or 10 picofarad. My output will be VR into x full scale, x by x full scale. So by using the relaxation oscillator circuit with totally 6 switches and one op-amp comparator and one op-amp and one op-amp integrator, we can get an output which is directly proportional to x from a floating Viper resistive displacement transducer. I stop here. I'll meet you in the next class.